Hi there, and welcome to an internet model of the Insular Cortex, Part 1A. First of all, you might want to check the previous video, which can be found on the address given on the screen, or alternatively check the TAWOP 2008 channel, which is spelt TAWOP 2008. So why develop a model of the Insular Cortex? Well, the Insular Cortex is an interesting part of the brain that hasn't been as well researched as a number of other brain regions. What seems to be emerging is that the Insular Cortex is actually playing quite an important role in the brain. Thus there is evidence that it has a role in bringing together the sensations and emotions we experience. The Insular Cortex is also being associated with a number of illnesses, and so a better understanding of its role could be of benefit. Historically also, the Insular Cortex is interesting. It was first named Reil's cortex after Johann Christian Reil, who, as well as identifying this part of the brain, was also the father of modern psychiatry. So here is a schematic cross-section through the brain. Imagine that you're facing a person, and then imagine cutting a slice through the brain as you're facing head-on, just in front of the ear, roughly. This is the schematic representation of what you would see if you did that. Moving first of all to the outer surface, we have the cortex in red. Tracing it round on the convex surface, and now we have the insular cortex. If you were looking from the side, you wouldn't be able to see it immediately. You'd have to move the other parts of the cortex out of the way. Here we have the claustrum next to the insula. This is a very mysterious part of the brain. Francis Crick, the co-discoverer of DNA, has suggested this is the seat of consciousness, as it has widespread connections throughout the brain. Here is the lentiform nucleus, which is a lens-shaped structure containing the putamen and globus pallidus, which form part of the basal ganglia, which is involved in movement. Here is the thalamus, which passes connections between lots of areas, and in some senses is a relay station, but there is actually some evidence that it processes information as well. So there were 3 studies that gave me an idea for this model of the insula. This is the first one by Cameron and colleagues in the Archives of General Psychiatry in 2007, and they were looking at GABA receptors in the brains of people with panic attacks and comparing them with people without. They were looking in particular at a neurotransmitter called GABA. So first of all, what is a GABA receptor and what is GABA? Well, the brain is made up of lots of building blocks called neurons that are very tiny. They connect to each other and pass information through their connections. If the first neuron passes information to the second neuron, we call the first neuron the presynaptic neuron, and the second neuron the postsynaptic neuron, which is blue in the diagram. Now, when the neurons pass information to each other, they use chemical messengers called neurotransmitters. One of these neurotransmitters is called GABA. There is a special type of receptor called a GABA receptor, which acts like the lock where GABA is the key. So first of all, the GABA is released from the presynaptic neuron. It then binds to the GABA receptor, opening it and allowing negatively charged chloride ions to pass through. Chlorine is part of table salts and added to water in swimming pools to keep them clean because of its bleaching properties. So it's a chemical that people come across in everyday life. The chloride enters the postsynaptic neuron and makes it negatively charged on the inside. This makes it more difficult to fire effectively, inhibiting this neuron. At the same time, the GABA is then taken back up into the presynaptic neuron. Now this is a gross oversimplification, and there are sometimes other consequences when GABA reaches the postsynaptic neuron, but we won't consider those here. Now in this study, the authors used flumazenil, which is a compound that binds to part of the GABA receptor, which is also bound to by a class of drugs known as the benzodiazepines. So in this study, the flumazenil was radioactive. When it bound to the GABA receptor, it released ionizing radiation, which was picked up by a detector in the PET scanner. Now what the authors found was quite interesting. There was less activity in the insular cortex in people with panic attacks than in those without. There were a number of explanations for this. So first of all, there could have been less neurons with GABA receptors in the insula. Secondly, there could have been less GABA receptors on neurons in the insula. And thirdly, other compounds binding to GABA receptors in the insula. Now, before we go any further, I just want to refer to a Pulitzer Prize-winning book by Douglas Hofstadter called Gödel, Escher, Bach, An Eternal Golden Braid, which was published just under 30 years ago. In this book, Hofstadter suggested that Euclid's principles of geometry came about as a result of small individual steps in reasoning, which occur very quickly because the brain is so good at performing lots of calculations very quickly. So for the purposes of building this model, I've attempted to break it down into these very small steps, which I refer to as assumptions. The neat point about these assumptions is that they can easily be challenged, which we will need to do to improve the model. So, returning to the study, I've drawn two assumptions. The first assumption is that GABA A receptors are less available in the insular cortex in people with panic disorder. The second assumption is more contentious and goes beyond the study data, but helps with the model. That is that in panic disorder, there is a direct result of there being less GABA A receptor availability in the insular cortex. We'll now continue to the second video. Welcome to the second part of this talk on the insular cortex. If you haven't already, you might want to watch the first part of the presentation before watching this video. So the next study I looked at was published in the journal Science this year and looked at people with borderline personality disorder in comparison to a control group without. Now I won't go into too much detail about borderline personality, but it's a condition in which a person can have difficulties in their relationships with others. They can also have difficulties in regulating their emotions. In this study, people were put into pairs and played a game in which they gave and received money. There were two main findings. Firstly, the process of give and take was more likely to break down if one of the pair had borderline personality disorder. The second finding occurred when they looked into the brains of people playing the game. When people received a gift from the other person, the anterior insular cortex would fire in anticipation. Now, when it came to people with borderline personality disorder, their brains didn't fire in anticipation. Instead, the right anterior insular's activity was dampened down. So we can say that people with borderline personality disorder have decreased activity in the anterior insular cortex when receiving gifts from their game partners. The authors thought this was because people with borderline personality were more suspicious of their game partners. This leads on to assumption 3. The anterior insular cortex is activated when people are receiving gifts from others. And to simplify it, the anterior insular cortex is activated when other people are relating to the individual. And also, people with borderline personality disorder have difficulties with emotional regulation and have less activation in the anterior insula when receiving gifts from other people. A big step now. Decreased activity in the anterior insula leads to difficulties in emotions in people with borderline personality disorder. Now, I was listening to one of the science podcasts, and this shows the possible benefits of this medium. One of the authors of the study, Lawrence Williams, was being interviewed. In his study, he found that if people felt something warm, they were more likely to give to others, and the reverse was true if they experienced cold temperatures. Williams discussed how the insular cortex might have been involved in bringing together emotions and sensations. When I listened to this, I put this together with the other pieces of information to come up with a model. So firstly, the assumption here, which isn't based on evidence at this point, is that the insular cortex integrates emotional and sensory information, although there is a lot of evidence out there if you look further. So here's the model. The model states that the intensity of emotions we experience is determined by processing that happens in the insula, and that this is in turn determined by the availability of GABA A receptors and also by the sensory input the insula receives. So how can you contribute? Well, there's a number of ways. You can offer criticisms of the model. You can offer criticisms of the steps that I've taken to reach this model. You can offer alternative models involving the insular cortex, offer new assumptions that can be used in the model, or just identify parts of the presentation which aren't very clear. You can also contribute by leaving comments on the Amazing World of Psychiatry blog, or video responses or comments on YouTube, or drop me an email to justinmarley17@yahoo.co.uk marked insular or insular cortex, and clarify if you want to be included on the list of contributors to the model. We already have one. Thanks very much for your time.
Hi, and welcome to Criticisms Part 1 of a Model of the Insular Cortex. So, in the process of refining a model of the insular cortex, I thought that criticisms would be an extremely important part of this process. For the sake of convenience, I've divided the criticisms that are possible into 5 main categories. Firstly, criticisms that occur at the level of the system of knowledge. So, for instance, in the area of neuropharmacology, there is already a vast body of knowledge, and the question we have to ask is, does this model fit in with what is classically thought of in that domain? If it doesn't, then perhaps we need to rethink the model. Secondly, is the model testable? Again, for practical purposes, since we want to have some benefit in the real world, this model needs to produce results which are testable. And this leads on to the next part. Data. Is there already evidence or data from studies out there which invalidates what the model is saying? First of all, the model has to be testable in order for us to be able to look at this data in more detail. Fourthly, are the elements of the model integrated together They fit together nicely. And finally, experientially, does the model make sense to us in our everyday lives? Does it tally up with our experiences? So firstly, let's have a look at the theoretical criticisms of the model. So the first point about this was the model doesn't specify individual emotions, but makes a general remark about emotions. So it's a little vague at this point in time. Secondly, the model doesn't distinguish between state and trait. So when we have emotions, we can have them at one moment in time, or we can have a tendency to have these emotions over a longer period of time. The model at this point in time doesn't distinguish between the two. And finally, the model doesn't have any reference to the limbic system, which, from previous knowledge, has been shown to play an important part in the role of generating and processing emotions. So now on to testability. Well, the model doesn't make any reference to outcome measures. Again, if we want to test this in the real world, we need to have some outcome measures that can be used to look at the model in more detail. So for instance, do we have any measures of the individual emotions which are referenced, any rating scales for instance? Secondly, the model doesn't specify a quantitative relationship between the three components that are already in the model, so it's difficult for us to know at this moment which way things should move. For instance, what happens if the sensory input increases? Does that result in an increase in the emotional sensation? Although there's some evidence out there to suggest this might be the case, the model hasn't made any specific comments about this at this point in time. Now looking at the data, well, the model's very crude at this point in time. It needs further refinement before we can look more closely at the data from experimental studies that have already taken place. Integration. The model contains references to sensations and emotions and also to basic pharmacology, but there's no link or causal pathway between those different elements, so that needs to be developed over time. Finally, does the model make sense to us experientially? Again, it's a little bit too underdeveloped at the moment to let us relate it to our everyday experiences, so there's still some way to go. So these criticisms will help to inform further refinements of the model. If you have any criticisms, please feel free to contribute them through a video response or by referencing the contact details on the previous video. Thank you for your time.